here's an interesting inference algorithm that we are now going to discuss. So far we talked about model checking. Then we talked about direct proof using a search algorithm and inference rule. Now I'm going to talk about an inference algorithm called resolution-based theorem prover. The reason it's called resolution-based is because it will only use one inference rule, which is the resolution rule, and we are able to achieve a sound and complete algorithm. Yes, the resolution algorithm uses the resolution inference rules. It is sound and complete. So we're going to use this rule here. That's it. And just using this rule, we are able to construct a sound and complete inference algorithm. So this is very attractive. The resolution rule only applies to clauses or disjunction of literals, right? So it only applies to sentences that look something like this, right? A disjunction of literals. That means our knowledge base sentences need to all be in this format, right? A disjunction of literals. The good thing is that any sentence in propositional logic can be converted to a disjunction of conjunctions, that is, into conjunctive normal form. So all we need to do in order to use this resolution-based algorithm, we just need to make sure that we take our knowledge base and convert it to CNF. So here's an example, just as a reminder. You've taken this in a previous class, but this is just a reminder. You will not be asked in the exam to convert a knowledge base to a CNF. So I'm just showing this as a reminder. Imagine this is your knowledge base. You can convert it to a CNF very simply by eliminating the biconditionals and changing it to implications. Then eliminate the implications and change it to the not alpha or beta type of format. Then move the not inwards using De Morgan's rules and double negation. And then finally distribute the alpha, the ors over the ands, right? And then flatten your clauses. So now you see we have this following clause, clause 1, which is disjunction, and then clause 2, and then clause 3, right? So this has converted this knowledge base to the following conjunctive normal form, right? So what is the resolution algorithm? Assuming we have a KB that is in CNF, conjunctive normal form format, recall that earlier we said the following. KB entails alpha if and only if you can show that KB and not alpha is unsatisfiable. So to establish KB entail alpha, what does the resolution algorithm use? It uses a proof by contradiction to show that KB and not alpha is unsatisfiable. The resolution algorithm works as follows. First step, convert your KB and not alpha to CNF. Then the resolution rule is applied to pairs of clauses that contain complementary literal. So remember, the way it works is as this. Imagine you had a KB. This KB contains sentences. These sentences are in CNF. This is your alpha. What you do is negate your alpha and add it to your KB. Why do we want to add it to your KB? Because if you add it to your KB, you get this KB and not alpha. Okay. Then your KB consists of clauses because you've already converted it to CNF, including the not alpha, which is also a clause as well in CNF format. What you want to do is you want to apply the resolution rule on pairs of clauses. So look at every single possible pairing of the clauses in your KB and apply the resolution rule, right? So take any two clauses, CI and CJ, apply the resolution rule to come up with some new clause. We'll call it CK, right? Add this clause to your KB as a new clause CK, okay? The resultant clause is added to KB. This is done again and again. So you keep, taking pairs of clauses and doing the resolution rule and adding new clauses to your KB. You do this again and again until the following. You take two clauses. When you resolve the two clauses, it yields the empty clause. This means that KB and not alpha is unsatisfiable, which means that KB entails alpha. So if you take two pairs of clauses, CI and CJ, and when you resolve them, it actually, evaluates to nothing, meaning the empty clause, that means that you found a contradiction. Okay, and it means that KB and not alpha is unsatisfiable. So we've achieved this condition, which means that KB entails alpha. All right. Essentially, what happens is you said the following. I already know that KB consists of facts that are true. Let me assume that KB and not alpha is a true statement. So I'm going to add the not alpha to my KB. If I did this and I run the resolution algorithm and I found an empty clause, that means that adding the not alpha to the KB resulted in a contradiction. And so KB and not alpha is unsatisfiable, resulting in a contradiction. It must be the case that since not alpha yields a contradiction, it must be the case that KB and alpha is true, right? And so alpha must be true, right? So KB entails alpha. Why does when does a two clauses resolve to yield an empty clause? Very simply, if you have, a literal P as a sentence in your KB, just one single literal, positive literal P, and another sentence not P that is also in your knowledge base. So imagine you're resolving CI and CJ, and you're getting new clauses CK, and you're adding them to your KB. If at any point you have a P added to your KB, and then another point where you had not P added to your KB, this is a contradiction because you're saying that P is true, and also not P is true. So when you resolve these true, it yields the empty clause, which means you've detected this contradiction in your process. Okay. What can happen is that you may not find this empty clause. And so if you add KB and not alpha to your knowledge base, you find no empty clause if you continue, resolving clauses. And so no new clauses can be added to the KB. This means that KB does not entail alpha. Does it mean that alpha is false? No. All it means is that I can't answer the question, right? So this is how the resolution algorithm works, right? You have a KB that consists of the knowledge base, your original knowledge base, and the not alpha added to it. And you keep taking pairs of clauses, resolving them, and adding new clauses to your knowledge base. At some point, either you're going to get the empty clause or no more new clauses are generated. And so you can stop your algorithm. And this algorithm terminates. It must terminate. If you start with a set of clauses and you resolve clauses and you add new clauses, at some point, there will be no more new clauses that you can generate. And so this algorithm will terminate. This type of algorithm is called a resolution-based inference algorithm. It is sound and complete for propositional logic. It is sound because the resolution rule is sound, and it is complete because of a resolution of a theorem called the ground resolution theorem. We won't go into the details. You won't be asked questions on this, but the whole point of the ground resolution theorem is that it says that the algorithm terminates. Either you'll get an empty clause or there are no more new clauses to generate. And for those who are interested, you can find this proof in page 246. So let's look at an example of how the resolution algorithm works. This is my knowledge base. It consists of this sentence and this sentence. And let's say this is my query. I'm going to convert my knowledge base into CNF. I've converted it. This is it. Sorry, this is it. This entire set of clauses. Right? So this is one clause, this is another, this is a third, and this is the fourth. And I'm going to also add not P as a clause as well, right? So this is my KB and not alpha right here. Now I'm going to repeatedly apply the resolution on these pairs of clauses, right? So let's say I did it. I took this clause, and I resolved it, and I got this clause, right? I take this clause, this clause and this clause. Sorry, I resolve this clause and this clause. It yields multiple clauses, actually. One way is to resolve the P2 and P2 here to yield this clause, or I can resolve it this way by taking out the B and it will yield this clause, or I can resolve it yeah, just these two, right? This two and this two here. Okay, and this is one. So just resolving these two clauses, this one and this one yields these two here. You can also resolve this clause and this clause. Then at another step, you can resolve this clause and this clause, this clause and this clause. At some point, what will happen is that you will resolve this clause and this clause. And what you'll get is the empty clause, right? What this means is that while you were resolving clauses, you've added this fact to your knowledge base, and this fact already exists to your knowledge base. You're saying that this is true and also this is true. And this is a contradiction. You can't have both of them to be true. And so it yields the empty clause. right? So with this, we've detected the empty clause, and so we can say that KB entails the original alpha, not P12. This is the pseudocode for resolution algorithm. You have a knowledge base, you have an alpha. Your clauses is a set of clauses in the CNF for KB and not alpha. And these are new clauses that you generate. You keep looping. For every 2 clauses in your clauses, you're going to perform the resolution. And for the possible clauses that are generated by the resolution, you will, if it yields the empty clause, then you can stop and you return that yes, KB does entail alpha. Otherwise, you're just going to keep adding these new clauses to your, right? This is it, clause. You add the new clauses to your clauses. If no new clauses have been generated, then you can stop the process, right? And you return false. KB does not entail alpha. Can we do better than the resolution algorithm? What we've just seen is that the good thing about the resolution algorithm, it just requires a single inference rule, and it is sound and complete for propositional logic. However, notice that we still have to resolve pairs over and over. The pair resolution process is still finite, but it can be exponential in the worst case time complexity. Just to give you a rough idea why this is the case, how many possible clauses are there if we have n symbols, right, or n literals? Each literal can be positive or negative, like P or not P. So total positive and negative literals is going to be 2n. We have clauses of size 1, right? Your clause C1, C2 can be just a single literal. It could be 2 literals. It could be of size n, right? So the total is 2n, choose 1, because you have 2n possible positive and negative literals. You want to choose 1. This is the clauses of size 1. This is the clauses of size 2, clauses of size 3, all the way up to the clauses of size n. This represents the sum of all possible clauses you can generate, okay, from the for n symbols, right? And this is around 2 to the power of n, right? So in the worst case, you might generate your loop here. This loop might loop on clauses of size around 2 to the power of n, plus you're looking at pairs of clauses, right? So it's exponential time complexity. Can we do better than this? Yes, if the sentences in your knowledge base are Horn clauses, then deciding entailment can be done in time that is linear in the size of the knowledge base, that is linear in the number of clauses and the number of symbols in your knowledge base. So there are 2 inference algorithms that operate on Horn clauses. They're very simple to follow. One is forward chaining and the other is backward chaining. They're very similar in nature, and they are both sound and complete. So what are Horn clauses? Very simply, a Horn clause is a disjunction of literals for which at most one is positive. So a single symbol that is a positive literal, like PQR. A conjunction of symbols implies a symbol. For example, P and R implies Q. So a Horn clause is a disjunction of literals for which at most one is positive. For example, this is a disjunction of literals for which at most one is positive, which is the beta. The Horn clauses can be written in the form of premises implies conclusion. Why? Because you can rewrite this as not premises or the conclusion, right? And this would be a Horn clause, right? Because this is a disjunction of literal for which at most one is positive. Given a KB of just Horn clauses, we can leverage the modus ponens inference rule, right? Because we may have a set of facts, which is alpha 1 to alpha n. These are just sentences. And because these facts are true, all these sentences are true. If we have a Horn clause that looks like this, premise implies conclusion, then because these are true, we can combine it with this sentence to imply that beta is true. So a knowledge base of Horn clauses typically use the following format: premise implies conclusion, and we can then leverage the modus ponens rules. This is sound and complete, and it is linear if you do this, right? So let's show the 2 algorithms I talked about that operate on Horn clauses. The first one I'll show is forward chaining, via an example, and the second one I'll show is backward chaining. So To show that KB implies Q or query, forward chaining works as follows. You want to apply the modus ponens, begin with positive literals, which are facts in the knowledge base, find a definite clause with the positive literals in the premise, and then add its conclusion to the KB. Keep applying modus ponens until the query, which is the goal, is achieved. So here is an example. You are given a KB with horn clauses. This is an example of a knowledge base that contains horn clauses, right? This is a horn clause, a horn clause, a horn clause, a horn clause, a horn clause. This is also considered a horn clause as well. It's just that it doesn't have any premise. Another name we also call this is these are the base facts in your knowledge base because they just contain facts. Okay, I want to use forward chaining to use this knowledge base to answer the following question. Does KB entail Q? We can do it as follows. Use forward chaining. We want to start from the positive literals, the facts. They become active in the and or graph, right? So we can represent this knowledge base as a graph. And this is called an AND gate. Why? Because you can see that for the literal P and the literal A, we are ANDing it here, A and P, and we're using it to imply L, right? So this is called an AND gate. This is called the AND or graph. Okay, so this is just an illustration just to show you how forward chaining works. We will maintain a set of actives as we prove. Until we reach Q. Okay. Start from the positive literals. So we look at our KB, we scan it, and we start from the literals that are just the facts. So we encounter A. So we're going to activate A, and so my set of actives becomes A. Okay. Then I'll scan my KB again and see if any query has been activated. Right? This has already been activated. And then I find the B. And so I can activate the B here because it's a positive fact or a literal hala. So it's a fact. So I'm going to activate B. Now I have two actives A and B. Then again, I start scanning my knowledge base, and I find that because A and B is active, I find that this query or this sentence here now becomes active, and now I can activate L because A and B are active. And so A, B, and L are now activated. Again, start scanning until you can activate one of the sentences, right? One of the premises in your horn clauses. So as I go down, I find that I can activate M because B and L are in my actives list. So I'll activate M. So on, I keep going. Now because L and M are active, I can now activate this clause or this horn clause, and so P becomes active. And then finally, when I scan this one, I find that P is active and now Q is now active. I activate Q. Q has become active. And so since Q has become active, I have found a direct proof using forward chaining that KB entails Q. And so this answer is yes. And so Q is true. Okay. And that is how you use forward chaining with a horn clause KB. What about backward chaining? Backward chaining works in a similar way, but it works backward from the query. Forward chaining works from positive literals and moves forward to the query. Backward chaining starts from the query, which is Q, and moves backward. It maintains a stack of sub-goals that need to be proved. And so when we start, this is our knowledge base, we will start from the query Q. And of course, the positive literals have to be among your already proved, and you just activate them directly because they are implicitly activated, right? They don't need any premise to activate them. So you'll have an already proved list, and you'll have a sub-goals list. So part of the sub-goals in the beginning is I want to prove Q, and what's already been proved is my facts, which is A and B. So Q needs to be proved. So I will scan my KB, and I find that in order to prove Q, I need to prove P. P has not been proved yet, so P will be added to my sub-goals. I now scan my KB sentence again, and I find where my sub-goals are part of the horn clauses. I find it here. So now L and M need to be proved. I continue scanning, and I find that B and L needs to be proved. And I also find that A and P needs to be proved, but these are already added to my sub-goals. And I also find that, L needs to be proved based off of that A and B is is already proved. Because A and B is already proved, I can remove L from my subgoals and add it to my already proved list, right? A is now added. Now, because L and B is added, I can remove M from my subgoals and add it to my proved list. Now, because L and M is proved, or proved to be true, I can add P to my already proved list. And then finally, I can add Q, right? So my subgoals is empty and my Q is now proved. And that is how backward chaining works. So both forward backward chaining are sound and complete for horn clausing. Both have a worst case complexity that is linear in the size of the KB, which is the number of clauses and the number of symbols. Backward chaining is goal driven, starts from the query and works backwards from the query. Forward chaining is data driven. It starts from the known facts and then moves forward toward the goal. In practice, backward chaining can cost less than linear in size of the KB because you might not need to process all the clauses, meaning as you accumulate your subgoals starting from your query, you may not need to add all the entire set of clauses to your subgoals. Backward chaining, because of this saving that might happen in practice, it is the common inference engine that is used in logic programming languages like Prolog, Knowledge Machine, and Eclipse. We'll show some examples of how to use Prolog. And many real-world problems can be naturally represented as horn clauses, which are premises, implies, conclusions. That is one good thing about horn clauses. This is a forward chaining pseudocode that you can find from the book. You start with a knowledge base that is in horn clause format. You have a query and use these data structures. I won't go into the detail, but the idea is that these data structures will allow you to keep track of, the set of symbols that you've already proved. And the set of clauses that you've encountered or scanned in your knowledge base at each point in the forward chaining. I should make it clear that this is a forward chaining implementation. And if you analyze this algorithm, right, what you notice is that you start with a queue of all the symbols that you're trying to prove. You have n symbols that you're trying to prove. And so given a KB with n symbols and k clauses, which is the number of horn clauses in your knowledge base, the while loop is on, meaning this outer loop is on because your queue starts with n symbols. And the number of possible inner loops, which is here, the number of clauses for every symbol you will loop on the clauses inside your knowledge base. This is going to be okay, linear as well in the number of clauses. And so the total num time is, this loop, and the inner loop here is onk. Like I said, I won't go into the detail, but it is more or less the same process that I mentioned that you want to do. Like if you're here and you have these actives, you start scanning your knowledge base until you encounter a premise that contains these actives for which you can add its conclusion. Right, that's what this loop is doing. Right, and so you don't need to know this, this algorithm in great detail for the purpose of the exam. You just need to know that given, if I give you a sentence like this and I give you a query, you can run backward or forward chaining in the following illustration that we have here. And with this, we finished talking about the inference algorithms that we want to discuss for propositional logic. So as a summary, right, this is a high-level summary. We have shown the following inference algorithms to establish entailment in propositional logic. You have model checking. This is truth table enumeration. The cost of this is 2 to the power of n, sound and complete. You have direct proof using a search algorithm with all inference rule. This is exponential because of the cost of the search algorithm. You have proof by contradiction using a resolution-based algorithm with a CNF-KB. This is sound and complete. Worst case is exponential. Forward and backward chaining with horn clauses. This is sound and complete, very attractive. These are linear in the size of the knowledge base. Most knowledge bases can be built with horn clauses. Are there more inference algorithms than this? The answer is yes. You can actually do proof by contradiction using modern SAT solvers. And in practice, these can be very, very fast for a large majority of your queries that you're trying to answer. These are backtracking DFS type of algorithms. One popular algorithm is called DPLL. The worst case is still exponential, but in practice, it can be extremely fast for a large number of problems. And you can find much of this discussion in 7.6, right? But for a purpose of exams, you just need to be aware of what we just discussed here. And as a reminder, for a general knowledge base, unfortunately, for propositional entailment is co-NP complete. This is probably no easier than NP complete. Every known inference algorithm for entailment in propositional logic has a worst case complexity that is exponential in the size of the input. So let's talk about SAT solvers right now. So just as a reminder, SAT is Boolean satisfiability. The problem is, given a formula, find an assignment of true or false to the variables in this formula that satisfies the entire formula. So it makes the formula evaluate to true. So in general, you have n variables or n symbols involved in this formula, and it is in propositional logic, and you want to satisfy assign true or false values to the symbols so that the entire formula evaluates to true. So SAT is NP complete problem. There is no known efficient algorithm for all cases. In practice, though, many formulas can be solved quickly using modern SAT solvers. So why is SAT relevant? Why am I talking about it right now? Why is it relevant to our topic of knowledge-based agents? Well, many problems can be modeled as SAT. Satisfying the modeled formula gives the solution to the original problem. This is because of the property of reductions of NP complete problems. For our purposes, for propositional entailment, we can use a SAT solver to determine if KB and not alpha is unsatisfiable. That is one way to show that KB entails alpha. Is if you can show that KB and not alpha is unsatisfiable, then you've shown that KB entails alpha. So we can use SAT solvers by giving it the formula KB and not alpha and see if it returns unsatisfiable. If it does, then KB entails alpha. Otherwise, if it returns a satisfiable assignment, then KB does not entail alpha. Here's a rough summary of SAT solvers. There are simple SAT solvers. These do sort of like a DFS tree enumeration of all possible truth and false assignment to the variables. We've already seen this algorithm. This is exactly what we do in model checking. There is this popular algorithm that was proposed back in 1962. It's called DPLL. This is from their authors, Davis, Putnam, Lugman, and Loveland. It is still a DFS tree enumeration, but it uses clever tricks to reduce the amount of subtrees checked in the full tree. Similar to what we did in backtracking, by doing clever heuristics and checks, we can avoid having to search the full tree. It's not guaranteed to always reduce. Worst case for general formulas is still going to be exponential. We'll briefly explain how this algorithm works. We'll talk about the 3 tricks that it uses. And then modern SAT solvers. These were initially inspired by the DPLL, but then more recent ones are inspired by a technique called CDCL. I put a link for those interested, which was proposed in '96. It is a popular research domain. It adds various tricks, caching, heuristics, and other optimizations to reduce the amount of work. Modern solvers nowadays can handle several millions of variables. And here's a nice link for a nice overview talk for those interested. And one thing to note is these SAT solvers, they assume that your input is a CNF formula. So you will need to convert your KB and not alpha to CNF, then run your SAT solver. So simple SAT solver. So what we'll cover is just these two, simple SAT solver and DPLL. So simple SAT solver, this is what I mean. Imagine you had this Boolean formula. What you want to do is a tree enumeration of all possible assignments of the variables. So we have 4 variables, A, B, C, and D. So pick a variable, assign it the 2 possible values, pick another variable, and you would do this in a depth first search manner up to the leaf where all variables have been assigned, and you evaluate, has this been assigned, does this give the formula, evaluate the formula, do these variable assignments allow the formula to be true or false? Because of what the SAT solver is trying to do, it is just trying to find a satisfying assignment. So if the DFS went down this path up to here, then that's it. It would return the solution at algorithm end. Otherwise, if it went down this path, it would find, this is not a satisfying assignment. It would try another path and then maybe another path and so on. Kind of like how backtracking works. This is 2 to the power of n, time complexity, and space complexity is O(n). What about DPLL? Well, DPLL does the same thing. It does kind of like a tree DFS search, but at each node in the search tree, it does some clever tricks. Here are 3 of the clever tricks. At each node, it uses the following tricks. Here's the first one, simplification. When a variable is assigned a true or false value, the clauses in the formula are simplified. Here's an example of what we mean by this. Let's say we had a formula and we assigned, let's say, the variable b to the value true in this formula, a or b or not c, and a or not b, and c or not b. Because we've assigned b equals true, then this formula can be simplified. How? Because this is now true. Anything ORed with true needs to evaluate to true. So this entire formula evaluates to true. This entire formula just becomes a, because not true becomes false and a or false becomes a. And this formula just becomes c, right? So this entire formula will simplify to a and c. That is what we mean by simplification. So whatever variable you've assigned, look at your formula and simplify it. Unit propagation. If a clause is a unit clause, and for those who don't know, a unit clause is just a clause that has a single symbol involved. This could be a positive symbol like P, or a negative symbol like not P. This would be just a clause with one symbol involved. This clause can only be satisfied by assigning the necessary value to make this literal true, or this clause true. Thus, no choice is necessary. So, for example, if you are looking at this formula here, this not B is a unit clause, right? And so there's only one way to make this unit clause satisfiable, evaluating to true. We need to take the not B and set B equals false, right? So whenever you have a unit clause, there's only one way to make this unit clause satisfiable, then do so, right? And then after you do unit propagation, you also need to, you can also have an opportunity to simplify the remainder formula, right? Where that is, remove every clause containing the literal and discarding the complement from every clause containing the complement, just as we did here. So as an example, look at this formula. We know this is a unit clause, so this is the unit clause not B. We must assign B equals false to get satisfiability. So after doing so, once we assign B equals false, this becomes true. And then we notice that this can also become true, and we can simplify this entire formula to just A. And then also this becomes false, and we can simplify this formula to A or not C, right? And so this entire formula, this then propagates and simplifies the formula to A or not C, right? Sorry, this formula will evaluate to true, right? So you have true, true, and then this becomes A or not C. Okay, so in practice, we can get more unit clauses after applying propagation. So we can repeat this unit propagation again and again, right? So this is a really powerful technique. You combined with the simplification, it allows you in the same node, right? You do this at each node. You can do simplification, unit propagation, and by doing unit propagation, this can result in a smaller formula, which you can then either do simplification or more unit propagation, right? And this all happens in the same node. And so in one single node, you can do a lot of assignment of variables. Finally, there's one more trick, which is pure literal assignment. If a propositional variable occurs with only one polarity in the formula, it is called a pure literal. As an example, what we mean by polarity, we mean by the sign, negation or positive. So not P would be a negative literal, and just P would be a positive literal. So if you have a propositional variable that occurs with the same polarity, then it is called pure. A pure literal can always be assigned a way that makes all the clauses containing it true. After assignment, we can simplify the formula even more. So for this formula that you see here, A is a pure literal. Why? Because A occurs as positive here, and that's it. So A would be a pure literal. B is not pure because it occurs here as positive and here as negative. C is not pure because it occurs here as positive and here as negative. So here A is a pure literal. You can assign a true or false value such that the clauses will be the clauses will be satisfied, the ones that are containing it to be true, right? So it's very clear here, because this is A is a pure literal. If we assign A equals true, it will evaluate this entire clause to true. And if you assign here A equals true, it will evaluate this entire clause to true. So assign pure based on their sign. So here set A equals true. If it was negative, we'd assign it to false. Simplify the formula to not B or C. Note that we now get not B as a pure literal and also not C. So we can even continue pure literal assignment again and again and again. So these are the three tricks. In terms of the structure of the algorithm, this is the node that you have in your tree. Inside the node, it will take the current clauses, right? This is the formula. The formula can be broken down into clauses. And at the first step, you can do unit propagation. While there is a unit clause in your clauses, just keep doing more and more unit propagation. The result of a unit propagation is a simplified formula. This is why we pass the clause and the unit clause. And we do simplification or unit propagation inside this function. And this results in a simpler set of clauses, right? It simplifies the formula. So keep doing this again and again and again and again until there's no more unit clauses. Then you can proceed with pure literal elimination. While there is a literal that is pure in the clauses, keep doing pure literal assignment and keep simplifying your clauses. And then you can have a stop criteria, right? Pure literal clauses and unit propagation contain simplification. After you do these steps, if the clauses is empty, meaning there's no more clauses left to assign, that means that you didn't have any clauses evaluate to false. And so all the clauses have been satisfied. So just return true. This is a satisfiable formula. Otherwise, if your clauses contains a false clause, meaning one of the clauses were evaluated to false as you were assigning variables values, then this path down here cannot be assigned. And so just return a false and backtrack to a previous step. Otherwise, if there are more clauses involved, meaning your formula is simplified, but there's still more variables that need to be assigned, then choose a variable to assign and then proceed down the left branch. This is when you assign that variable the value true, or down the right branch. This is where you assign that variable the value false, right? And so on, right? So this is just proceeding down the tree. In practice, this can still, this should be a fast algorithm or for the majority of problems. However, in the worst case, it can still be 2 to the power of n in terms of time complexity. Here's just another illustration of DPLL. Imagine this was our formula. This is our root node. And let's say we went down the left branch. We assigned the value not A. At this node here, we've assigned A the value false. So after branching on not A, where A is assigned the value false, unit propagation of the clauses A or not B forces not B. So when we go down and we set A equals false, what happens to this formula? This formula now becomes simplified to the following. False or not B just evaluates to not B. This evaluates to true. And this will evaluate to C or not D. This evaluates to not C or not E, and this stay the same, right? So it's only this that becomes not B. This evaluates to true, so it gets removed. This evaluates to C or not D, and these remaining stay the same, right? So if you look at this, after branching on not A, so this is the simplified formula here, unit propagations of the clauses A or not B forces not B, right? So this now becomes, we can continue and unit propagate on this formula because now we have a unit clause which is not B in the formula when we're at this node. So because we have a unit clause, we need to set B to false, right, to satisfy this formula. So there's no point. This is why this child here or this node here only has one child when we set B equals false. Right? There's no point in going down the path where you set B equals true because it will make the unit clause evaluate to false. Another example that we see here is when we branch here and we set A equals true, then this evaluates to true. This here evaluates to C or not D. This evaluates to true. This, and stays the same. Notice that we no longer need to consider the B branches, right? There's no point in assigning B a value. Why? Because you can see that the B value has been removed from the remainder formula, because now this is just a true value, right? So this subtree is now one level smaller, right? So I didn't go through all of it, but it's the same matter. At each node, you have opportunities for unit propagation, simplification, and pure literal assignment, and so on. There's a package called PySat. This is a Python package. It contains various solvers. It supports proposition logic formula. I won't go into the detail, but I show you here how you can write the formula for the format that it wants to look at for this CNF formula. So not x1 or x2 is written as -1, 2. This is the first clause. The second clause is not not x1 or not x2 is written at -1 and -2. And then you just set up your solver. You pass it the CNF. You set up the type of solver model that you want, and then you say solve. This is where you set up the solver with this CNF, and you solve, and then you can get the variable assignments that you want. These are all the solvers that are available. These are popular modern solvers that are available. What I wanted to show is just I ran experiments for PySat. I generated random 3 CNFs. These are CNFs, or sorry, formulas that contains clauses where that contains 3 variables only in each clause. I used 2 modern solvers, Glucose and Minisat, and limited to 60 seconds. And I just wanted to compare the runtime executions for random 3 CNFs. These are the number of variables. These are the number of clauses. So at 100 variables and 500 clauses, you can see that both algorithms are both solvers have comparable times. 150 variables, 200 variables, 250. Once we get to 300 variables, you can see the difference. And then at 400 variables and 2000 clauses, you can see that Minisat is starting to overtake it, right? Again, these are both modern solvers. They use tricks and heuristics. They're not guaranteed to always reduce the time, but even at 400 variables, we get a good amount of speed up in seconds. Okay, these we've talked about using proposition logic. What about other logical languages like first order logic? This can definitely be used. So proposition logic has a couple of positives, but it also has a couple of drawbacks. And mainly it is the limited expressive power. So with the Modbus world, for example, when we wanted to say to have in our knowledge base this mechanic that pits can cause breezes in adjacent square. Just for one grid location like B11, we needed to have this rule inside of our KB. For every single grid location, right, you will need to have a similar rule, right? So this will cause, a huge number of rules that are added to your knowledge base. Another thing is that it can't deal with changes in facts over time. If you are going to model your environment at each time step and add those facts at each time step to the knowledge base, then you'll need to use a symbol per time step. It is also difficult to represent the relationship among objects and properties and things like this. So it has limited expressive power. We need a more expressive language with inference capabilities as well. What we can do is we can also use first order logic, and first order logic does have inference algorithms with their own properties as well. Or we can use second order logic and so on, right? Another thing that PL doesn't account for is is uncertainty, right? So we need a framework for uncertainty, and one thing we can use for that is probability theory. So in terms of languages, we use proposition logic, but we could have used first order logic. It gives us more expressive power, as well as some other type of logic. But for this course, we will talk about in the next topic how to use probability theory to model uncertainty about the facts. So instead of saying, is there a pit at location, I and J, with proposition logic, this is either true or false. But with probability theory, we can say, what is the probability that there is a pit in I and J? And so we can get a value between 0 and 1. Just as a summary of what we can do with first order logic, we can express a lot of rules in first order logic in a more concise way. So typically we can present the precept as a predicate where we say, is there this particular precept at time step 5, for example, or time step 6. So this allows us to express this simple rule inside of our knowledge base that takes in a vector of precepts and a time step and evaluates this to true or false. Actions can also be represented, whether or not the agent took an action at a particular time step. Furthermore, for the perception rules about the breezes and the glitter, we can have it using quantifiers like for all and there exists. These are things you've already taken. This is how to have a simple reflex behavior. If there's a glitter at any time step in your current location, then just take the action of grabbing it. I'm going to skip this. This is some technical detail related to first order logic, not required for the course. This is just for your overview of first order logic. Another thing I wanted to talk about is the rule for the breezes. Adjacency of two squares can be defined as this. And furthermore, we can define the breezes using this adjacency rule using this, right? If an agent is a particular location and there's a breeze, then this applies to the breeze at this particular location. And you can also define similar way the logic for or the first order logic for having a breeze at a particular location and there being pits in adjacent locations. If you want to look at the full breakdown of the FOL language for this Wampus world, you can find it in the book. We won't really be focusing on first order logic. I just wanted to show how expressive it is at expressing different rules for the Wampus world. If we wanted to present the Wampus world in proposition logic fully, we have an n by n grid that's n squared proposition for the pits, 4n squared proposition for the breeze mechanics, n squared propositions for the Wampus, 4n squared propositions for the Wampus mechanic with the stink mechanic, n squared propositions for the gold glitter. So for max of t time steps, you're looking at 12t n squared. KB entails alpha, then the algorithm generates the empty clause. If KB doesn't entail alpha, then the algorithm will terminate because there's no more new clauses to generate. That's what we saw with the resolution algorithm. What about first order logic? In first order logic, resolution is actually refutation complete. What this means is that for any formula that is in first order logic, if we wanted to use a refutation or resolution based algorithm, if the KB, now our KB is in first order logic, right? If the KB entails alpha, then the resolution-based first-order logic algorithm will generate the empty clause. However, for some formulas, if the KB doesn't entail alpha, then if you run the resolution-based first-order logic algorithm, then this algorithm may never terminate. However, as you run the algorithm will take a long time while it's running. You don't know if the KB entails or doesn't entail alpha. It could be just that it takes a long time to run, and at some point it will generate the empty clause, right? So the issue with first order logic is that you don't know if KB doesn't entail alpha for some formulas because your algorithm will just continue running and may never terminate. For those interested, you can read the chapter about first order logic to read the technical details for this. But for our case, I just wanted to show the difference in terms of the resolution-based algorithms. This is related, for those interested, to the decidability of the logic language. Propositional logic is decidable, whereas FOL is semi-decidable. And again, this is going into the technical details. For I would say for the purpose of exams, you might get questions true or false up to this level only. In terms of programming languages that allow us to use logic, there is the Prolog programming language. This is a logic programming language. It supports some format of first order logic. It uses horn clause representations. It uses backward chaining for its entailment proving. And due to the way backward propagation is implemented in Prolog, it can actually get stuck in some infinite loop for some entailed queries. So in class, I will show how to use Prolog to navigate an environment that has pits. So with this, we would stop our topic in terms of the things we want to cover. وجزاكم الله خير والسلام عليكم ورحمة الله وبركاته.